So it's a pretty long title. I'm going to get into the title a little more in detail, because these are the two most important things in my company. One is the fear of my boss, so as usually, but I'm not going to talk about my boss today, but about this little tiny laser you see here. This is this small spot there, and the active region really is only under here. So we're talking about a very small semiconductor device. And I hope I can teach you a little bit about talking about costs, about tunable lasers. I'm going to present some gas modules, some are for high volume applications, presenting also some other applications. We're using DFB, meaning distributed feedback lasers. So I hope you're going to learn a little bit about DFB lasers. And they're used in the near-infrared spectral regions and in the mid-infrared spectral regions. So the whole area is called Tunable Laser Absorption Reference Spectroscopy. That's TDLARS. I'm getting into advantages about the MIR sensing against the NIR using Interband Cascade Laser. So getting more into the deep, this is what was on the finger. And under this small portion here, enlarged, you see a picture of a rich waveguide laser, which has gratings to both sides. So here you can see this is about 1 micrometer, and you can see the small grating steps here. So it's getting really into deep into nanotechnology. It's even getting smaller. This is the size of a nanometer, and you can see here the crystal indium arsenide on the one side and aluminum antimonide on the other side. This is how the distributed feedback laser works. You have the active region here, and the polychrome modes are formed by the rear and front set of the semiconductor device. This is giving you polychrome modes like this, so every little spike here is an allowed polychrome mode of this device. And we want a single mode, tunable laser. This is why we have a selective lateral metal grating here, which is selecting, which is suppressing all the modes which we don't want, and only the mode with the lowest losses is the mode which is lazy. You have a nice single mode laser here with a side suppression in the order of 35 degrees. And this laser is tunable, which is on the next slide. So we tune this laser by current tuning, which is corresponding to wavelength tuning. So in this case here, it's about 3 nanometers. And every time the laser is going to this time, in this case, 2.740 micrometers, these water molecules here will start to do vibrational rotational transitions. So this is what we are detecting with the laser. On the other side here, the photodetector, the laser goes through the molecules and they're vibrating. That's the absorption spectroscopy that we are detecting. There's, of course, all kinds of other gases. So oxygen is 760 nanometer. There's a strong water vapor line, 1877. CO2 exactly at 2 microns, or carbon monoxide 2.3. And there's other gases here at 3 to 6 microns in the mid-infrared region that we are, our customers are using for their spectroscopy. If you're interested in other gases, I also have a booth in the exhibition area. You can come to visit me on my booth, ask me all kinds of questions later if you like. So why do we go to the mid-infrared region? Between 3 and 6 microns, they are extremely important molecules for gas sensing. All these different molecules, here are just a few examples. In the near-infrared, carbon monoxide has a absorption feature, but it's much stronger, or 2 orders of magnitude stronger here in the mid-infrared. And there's also other gases which only have strong absorption features in the mid-infrared, like NO2 or S2. So this is how the device looks. It has a small TC and an NTC. So you can control the temperature, stabilize the temperature. You tune the current. If you tune the current in this example between 20 and about 100 milliamps, and you tune the temperature between 10 and 50 C, you can get to lines between 3546 and 66. So about 20 nanometers of continuous tuning. And so you can select, in this case, one of these formaldehyde lines for your spectroscopy. Which brings me right to some applications. Formaldehyde is interesting in wood production. So this is the wood, you produce wood, and you want to detect how much formaldehyde, which is toxic to humans, is in my wood production and then in my final product. So if we get it out of the wood early, it doesn't get into your room if you stay healthy. One of our customers, Aeroptic in Poland, they developed this sensor here. It's a retroreflector, so it goes out from the retroreflected, detecting the molecule, and they get 40 parts per billion in sensitivity. There's some other application examples here. So ethane, company Aerodyne, they're detecting ethane in methane. So they're detecting the amount of ethane in my methane concentration. And that changes with the source. So in that case, we don't have any ethane on the different methane concentration that comes from a landfill, or you can detect is it coming from a natural gas pipeline leak, or is it coming out of the mouth of a cow. Another application for process industry, SO2 detection. You can see the detector and the sensor here on both sides of the stack. The gas is going through the stack, and the company NIR monitors there in Norway. They are detecting the SO2 content in this stack. An example out of automotive. Here we have the car, and they look at the exhaust gas, NOx, CO, CO2, and also other gases. Company in Germany. Since the Volkswagen, my boss is always putting the Volkswagen here. I have a Swedish car there. I don't know how good they are. Another application example, a very big project that's called DATS, driver alcohol detection. There's many car companies involved in here. It's two systems. One is a touch-based system. So the driver is starting the car, and the car is making a measurement of my blood alcohol content. So if I'm drunk, if I have too much alcohol in my blood, the car won't start, and I'm on the way, I'm able to drive away. So it's safe for everybody else, including me. And the second system, which is under test, is a breath-based system. So you create the car is collecting the breath out of your mouth, and this way detecting the alcohol content in your blood. So there's different applications. Of course, a breath-based system, not only alcohol is important. For this example, I think it's pretty clear that there's a lot of amount of alcohol coming out of fuel systems, but there's also other applications for breath gas analysis and for medical devices. So there's a lot of these things investigated. Let's try to spend some time in comparison of different gas detection technologies. So on the low-end side, there's electrochemical sensor or metal oxide sensors. Then on the other side, you have tunable laser sensors, which are very high detection limit and very good in selectivity. Cavity ring down spectroscopy, maybe some of you will know. And you can get a talk from me if you come to my booth and then you use Facebook, get a talk, so you don't have to take pictures anymore. So on the bad side of these sensors, they have poor selectivity, large crosstalk, and the worst of all, they really produce false alarms, right? So you get an alarm, and nothing is really going on. You get another alarm, nothing is really going on. You will put down the sensor like using that voltage can be quite dangerous. On the good side, they are very cheap. You can get them between $10 and $40. And on the other side, these sensors, they don't produce false alarm. They have very superior selectivity, but on the bad side, they're very expensive. Can cost up to $10,000, $15,000, even more, the more sophisticated. So we want to have an in-between technology, which is the NIR. It's available on the market since a few years. They're really good. Still, they can produce false alarms, which can be quite dangerous. So we developed with some customers TBL system with a reference cell inside, which don't produce false alarms, still for still for the same price, about $150 to $300, depending on the volume, of course. This is how it looks. You have the laser diode here, small collimation lens, adjustable mirror, so you can also adjust the length, reference health of the diode. And yeah, we made some measurements with that. I'm going to skip this slide because I think this is more important. In this field, you have fixed point analyzers. They cost something like $10,000 to $15,000. This is where tunable diode laser spectroscopy and laser is very established. And we would like to get to more in this direction, high volume markets, small sensors, variables, 100,000s or even millions of sensors every year with this technology. Point of care medical applications very high, where you need sensitivity and you need good reliability. So I hope I was able to give you some overview about talking about casts, tunable lasers, high volumes, and I think the cost efficiency is that what you really need most, right? So there's, for example, one can think of a sensor that everybody would really like to have, but maybe it would only be one sensor because you only need it very, very seldom. It may be very, very expensive, like $1 billion, but still be extremely cost effective because if you could really sense what you're trying to find out, it would save a lot of cost. So if you have this application like that, please come to my booth, discuss that with me. I can think of who's the better president sensor. I don't know if breath analysis would really make it, but anyway, thank you for your time.